Question 14. The diagram below shows the tensile stress strain graph for four materials A, B, C, D up to their breaking stress. So this point, this point, this point, and this point all correspond to the breaking point for each of these materials. So this is a stress strain graph, and the gradient of this graph represents the Young's modulus, and the peak, the top positions, the highest maxima represent the ultimate tensile stress as well. So the highest possible stress that the material can handle. Okay, so it starts off with looking at definitions and definition of stress. If you write down the formula to help us here, stress is equal to force over, and this here is key, it's cross-sectional area of the material. So it's the force, tensile force per unit cross-sectional area. So tensile force per unit cross-sectional area, that's the definition. The second definition is for strain. So write down the formula. Strain is equal to the extension over the original length. So is the ratio between the extension to the original length. Okay, so you could have said extension divided by original length as a definition there. So which identify property of material A using evidence from the graph to support your choice. So material A, if we look at it, there is no curvature, so that corresponds to there's no possible plastic behavior. Okay, so anything beyond an elastic limit, there's nothing there. So that could only mean that this material is brittle. Okay, so brittle materials often straight line, nothing after that, no curvature like these A, B, C, and D. So there's no plastic region. There you could write also there's a sudden breakage with no prior warning, and high stress with a small strain. So you can see there's a high stress and there's a very, very small strain. So meaning that the material doesn't really extend by much at all before it breaks. And for it to even extend by a small amount, a large amount of stress is required. And those are the properties of a brittle material. So the next part, it's a calculation. So a cylindrical specimen of material under test has a diameter of this and a breaking stress of that. So two pieces of information have been given to you, and it's stress and diameter. So it wants the tensile force in this part of the question that this specimen is under at its breaking point. So this material, this value becomes important because this is a value corresponding the breaking point. So the stress is 1.3 gigapascals. If we knew the cross-sectional area of this cylindrical specimen, remember it's a cylinder, so the cross-sectional area of a cylinder is a circle. Okay, so the cross-sectional area of a cylinder, that there is pi r squared, which is the cross-sectional area. Okay, so now what we look, they've given us the diameter and it's in meters. We halve it to get the radius, square it and times it by pi, we get the cross-sectional area. And if we want the tensile force, we just rearrange that equation. Force is equal to the tensile stress. So in this case, is the breaking stress. So that's 1.3 gigapascals multiplied by the cross-sectional area, which is pi, times by, that's the diameter, so we have to halve it and square it to get the cross-sectional area here. And remember, it's gigapascal, so that's 10 to the 9 pascals. You have to expand that out. And what we get as a force is 22.97 newtons to 36 figs, if you want to round that up, is 23.0 newtons. So key is to recognize that this is a cross-section area and because the diameter is given, we have to halve it to get the radius and apply pi r squared to get the cross-sectional area for that. And this here, the stress, it is not in pascals, it's in gigapascal. We need to do a conversion there as well. So what we've got is, in the next part, we've got the original length of this specimen is 1 meters, and that specimen under stress extends by 7 millimeters at the breaking point. So again, this breaking stress is now relevant because the breaking point, this is the stress, 1.3 gigapascals. We know it asks for the Young's modulus of this same material. So Young's modulus is the stress divided by the strain. So if we want to look at the breaking point, that would be the breaking stress here, and we know that's 1.3 gigapascals from earlier on in the question. So 1.3 gigapascals, so that's 1.3 times 10 to the 9. The strain is the extension divided by the original length. The extension is 7 millimeters, but because the length's given in meters, we got to convert that into meters as well, which is divided by 1,000. So 7 times 10 to the minus 3. As the extension, the length is 1 meter, so we divide by 1. So that's still 7 times 10 to the minus 3 as the strain. Put that here, and what we get is a Young's modulus of 1.86 times 10 to the 11 pascal. So there's your final answer. If you wanted to quote it in gigapascals, which is times 10 to the 9, take out a factor of 10 to the 9 here, you're left with 186 gigapascals. The next part of this question is a 6 marker, and what we have to do is we have to discuss which of the 4 materials shown in the graph is most suitable for the following applications. So a cable supporting a lift in a tall building, and a rope or cable attached to a person in a bungee jump. So let's split that 6 mark into 2. 3 marks for that, 3 marks for that. Okay, so let's have a look at the graph. Let's see which one will be suitable for the lift. So a lift has passengers inside it. It also has the weight of the lift that the cable has to support. So in terms of weight, it's a large amount of weight compared to just a bungee rope. So if it has a large amount of weight, which is a force, therefore the cable will have to have a large amount of stress before that cable can break. The only 2 options I see are B and C, with very large stresses. So B has the largest amount of stress, so I would go for a B because B has the largest amount of stress. You could equally have chosen C because the graphs are relatively similar. So let's have a look at what we could write for the justification for choosing the cable with the material B or C. So large loads will be used in the lift. Therefore, the cable is under large stresses. Okay, B is under large stress. B has the highest breaking stress compared to all the others, and we have to make a comparison. We have to discount all the others. So that word highest identifies that it's greater than A and D, so and C as well. So that's a relevant point. Now, this is another valid point. So tall buildings, that's what it says here. So we need a long cable. So the cable can't extend by much either. So which you don't want to stretch too much at all. So the cable you don't want to stretch. So you want a very low tensile strain, because the strain is to do with the extension, the fractional change in the extension. So long cable, you don't want it to extend much at all. So you want a low strain. So when we look at B, B has a relatively low amount of strain even for its maximum values. I would go for B rather than C because we can see that C does have a large strain for large stresses, but that could be an advantage as well because that's a prior warning before that cable could break. Okay, so it is an advantage or a disadvantage. You can add those points in as well. So B has a low tensile strain for a high tensile stress. So these are valid points that you could mention that will pick you up marks for C or B. The rope that we would choose, the material for the bungee rope that we will choose is D. And the reason is that the load is lower than a lift, as the mass of a person is significantly smaller than the mass of many people and the lift. Therefore, lower stress is required. Okay, so compared to a lift, a bungee rope will require less stress under tensile stress. So if we look at the graph, we look at the rope that has the least amount of stress. So D has a low amount of stress. So what else is going for material D? The time it takes for a person to come to a stop. We can't have the person come to a stop instantly as they fall. Otherwise, what will happen? Rip your limbs off if that would happen, and there'll be a large force on the actual body if you were to decelerate at a very fast rate. So what happens to compensate is the rope starts to stretch when it extends fully, and that means that the time it takes, the rope is extending for a significantly long time, and that reduces the impact force. So the tensile force is inversely proportional to the impact time. And we know this because if force is equal to the change in momentum over the time, we can see that the force is inversely proportional to the impact time. So if the longer it takes for an object to come to a stop, the lower the impact force is on the object. So the only way to achieve this is for is low tensile stress and a high tensile strain. So we want the rope to stretch, and that wouldn't mean that's a large extension and therefore a large strain. So if you look there, low stress, high strain, D is a good option for a bungee rope. And the last point I mentioned is large extension will allow time required to slow down safely as well. So that's an additional point that you can throw in as well. There are more points that are on the mark scheme. So if you want to have a look at the mark scheme for more points, you can.